All right, here we're looking at trigonometric word problems. These are going to be a little bit more complicated just because anytime you're using raw data, the numbers are a little bit more complicated. So here we have the number of daylight hours for Bell Buckle, Tennessee, depending on the day of the year it is. So we have a maximum at day 172, June 21st, of 14.5 hours of daylight. And then of course the shortest day of the year is way over here, day 355, coming in at 9.75 hours of daylight for that day. So if we want to answer any questions concerning this, we first need to build some kind of equation, which is usually the first question. So same kind of decisions need to be made here. This daylight hours follows a sinusoidal pattern, so we can pick a sine or cosine graph just with a lot of manipulatives to generate this actual data relationship. So sine or cosine, it kind of looks like it's starting at the trough down here at the y-intercept, but you gotta be real careful with that because it gets really, really flat. So it kind of looks like it could be the trough when it actually isn't. So seeing something that's labeled as a trough, I could compare that, the distance between a crest and trough, and see that the next trough, the first trough, is actually behind, not the y-intercept. So a negative cosine template might not be as easy as at first glance. So because of that I'm going to go ahead and jump all the way to a positive cosine template for this guy, right? The crest. I can clearly see it's labeled as a data point, so I can trust those numbers. I'm going with positive cosine. From here, I'm going to first calculate my amplitude, because that's going to help me find the axis of the wave. So amplitude is the highest y term minus the lowest y term. And then we're going to cut that in half for the actual amplitude. So the range here for this daylight hours is 4.75, which means the amplitude being half of that clocks in at 2.375. And that is half of my range, which we call amplitude, 2.375. That helps me find the axis of the wave. I know it's 2.375 above the crest or below, above the trough or below the crest. So 14.5 minus or 9.75 plus that amount will tell me my K term, which is now 12.125. Other things I have to find, my H term. How far did I have to shift this over to get to that positive crest, positive cosine template? 172 days. So minus 172 days will ensure I shift to the right 172 to match that. And the last thing here is going to be our B term, which depends on the cosine's typical period of 2 pi divided by the period I observed. Now again, we already said this wasn't the trough, so I can't go from here to 355 and call that the period, right? The trough is actually behind the y-axis. So the best way to do that again is go crest to trough, find how many days that was, and double it, and that'll give you the true period of 366 in this case. So I could reduce that down a little. I don't want to make a decimal out of that, but I'd certainly divide both of them by 2 to get 183, pi over 183. So now I have all the components to build my cosine wave to represent this relationship I got going on here in real life. So here we go. Y equals my A term, 2.375. Cosine is what we based everything off of. B term is pi over 183 on the outside of x minus 172. And my K term finally comes in here at the end, plus 12.125. So this equation, though it's long and complicated, I could plug in any day of the year and it would output the number of daylight hours corresponding to that day. And that allows me to answer other questions, other follow-up questions they might have, such as, during what period of time is the amount of daylight hours at least 12 hours? So here's the equation, complicated as it might be, between x and y. They're saying, when does y equal 12, what will x have to be? So x is over here buried in the equation, lots of things happening to it. We have to do them all in reverse PEMDAS order. So the first order of business is to get rid of this 12. That's going to kick this down to negative 0.125. The rest of the equation still remains. And the next weakest operation to go is going to be that multiplier out front of cosine. So I'm going to divide this simply by 2.375, and that's going to go down to negative 0.0526. I've now got myself down to the cosine function, and I need to think about how I'm going to get rid of that cosine, right? These are all these are all being cosine, so I first need to inverse cosine both sides. So inverse cosine will take care of that. Inverse cosine of negative 0.0526 is 1.623, and now I'm inside the cosine function, and I can continue to follow my reverse PEMDAS order. So because these are in parentheses, this multiplication would be the next weakest thing and have to be divided. I'm dividing by pi over 183. All right, if I plug that in the calculator, I got to divide by that whole parenthesis fraction there. And so x minus 172 is going to equal, on this side of the equation, 94.57. And then finally, to get x by itself, I need to add 172 to both sides. And I finally get that x is equal to 266.57. So x is the day of the year in which I have 12 hours of daylight. 266, that seems pretty reasonable to have 12 hours of daylight. It looks like it's lining up pretty much with my graph. Now I realize that that's only one time a year where it's actually 12. If I need the amount of daylight hours at least 12, above 12, then I realize it's going to happen again over here. And the easiest way to do that is to calculate how far you are from your crest and simply mirror that, because there's a very symmetrical bell curve here. So how far away am I? That would be a 94.57 days from my crest, my most daylight hours. And so I'd simply take 94.57 away from that crest, and I'll get an equivalent symmetrical answer of 77.43 days. So here are the 2 days a year in which it is exactly 12 hours. So to answer my question, what period of time is the amount of daylight hours at least 12? Between day 77 and 266.